1, 2, is this on? One, two, is this on? All right. Let me try to continue with this practice of quadratic reciprocity. And just so y'all know, my wild, wild imagination, this practice of math makes me think of that great Heroes of Might and Magic. Was it 5 or 6? The Archangel Michael and the dragon, the yellow dragon. Someone told me that there was kind of like some Italian words on this video, and it said that the yellow dragon blesses Michael with near omnipotence, nigh omnipotence, pretty much omnipotence for what this angel Michael is trying to do with such a long sword. Anyway, I'm gonna link that. It was just since 2014. The year 2014, I had, and I still have this MacBook Air, and it is just so cool to have this Heroes of Might and Magic, Michael the Archangel desktop wallpaper, and still, still I have this sense of gold and silver, might and magic, and I just want to let you know this is what I'm thinking as I try to learn this quadratic reciprocity. All right, let me try to do something here. All right, so I'm hoping I turned on my black light, my dark light, my purple light. I hope it fluoresces a lot of the things in my room here. Hulk. Okay, so as a child, Hulk is my favorite. The Incredible Hulk is my favorite superhero. I was just like on the playground. We were all like, which superhero are you gonna be? Which superhero are you gonna be? And then for me, I was like, it was a cross between the Silver Surfer, which is pretty much overpowered, and Hulk, who is also kind of overpowered. But as an adult, I really have liked Hulk less. As an adult, I just don't think I have this thing with being angry all the time. And it was just as an elementary school kid, I was like, man, they say that Hulk gets more and more angry if you do a one-on-one fist fight with the Hulk. And I was, the more angry he gets, the stronger he gets. So I was just like, I was blown away by the theoretically unbeatable Hulk in a 1 vs 1, because in a 1 vs 1 fist fight, you hit the Hulk, he gets more angry, he gets stronger. It's just like, how do you win against that? But as an adult, I don't really like the Hulk that much usually. I did play Hulk a lot in video games. Marvel superheroes. Hulk is very, very prominent. So I still have some useful memories of the Hulk. And still have useful memories of Silver Surfer. I don't know how all these tangents got into this video, but here we are. Let us assume Michael into our brain as we try to learn this. All right.
Z4. Here's Z3, and here's.
Okay, so previously I did a formula to get these, but now I'm going to do this by hand because I think it's more useful. So for my practice, I'm doing this by hand. I'm not using no spreadsheet formula. So I did 5. I redid the spreadsheet by hand before starting this stream.
That 2 process works for any integer greater than 1. Here are the tables for the ring Z4. Here's that.
Alright. So, alright, Z4. And the $1 billion question is, what is Mythologer thinking with his color scheme? That is the most important question. Alright. Anyway, okay. This is math practice. 4 plus and 4 times. The ring of 4 plus and 4 times. Now 1, 2, 3, 4. 1, 2, 3, 4. Oh. Yeah, everyone's got their way. I'll just have my way of doing this by hand. Sorry, I'm streaming. I'm gonna be finished at some point, not too long.
Good. You can stop anyone though.
Sure. Huh. Gosh. Oh my goodness. So I really messed up these tables. Yes. Gosh. Alright.
3. And here's Z2. So one ring for every integer greater than 1. Now, each of these rings contains only finitely many numbers, and the arithmetic of these numbers is a little warped. Nonetheless, as I already indicated, the addition and subtraction and multiplication in these rings works very much as usual. A plus b equals b plus a. You can expand brackets as usual, and so forth. So if you haven't seen these rings before, here's a small but very useful challenge for you. Take one of these rings, say Z5, and prove that the two basic laws over there still hold true in that ring. You do it. Now it also turns out that if our mini ring is based on a prime number, and it has to be prime, no other number will work, then our mini ring is super nice. In a prime mini ring, we can do addition, subtraction, multiplication, and also division, as usual. That is, the inverse of multiplication also makes sense in a prime mini ring. These special prime mini rings are known as fields. And yes, there are more familiar fields as well. The world of rational numbers is a field, and so are the real numbers and the complex numbers. And then things get really interesting, because a lot of the maths that builds on everybody's favorite field, the real numbers, have counterparts for these finite fields and rings. Plane and spatial geometry, vector spaces, and believe it or not, even to some extent calculus and things like surfaces. In fact, there are whole branches of mathematics that deal with finite geometry. I used to be really into finite geometry, and actually my first book was about visualizing finite geometries. I'll say a lot more about this in future videos. Now, just quickly, here are pictures that capture some of the abstract beauty of 4 geometries constructed with this mini field Z2, whose tables you can see over there. There are just 2 numbers in this field, and yet it gives birth to all this complex and beautiful stuff. There's one guy, another one, that's called a doily. That's a hexagon, believe it or not. And that's the smallest perfect universe. Anyway, The first thing I want to stress to help motivate what's to come is that these little relatives of the real numbers are super beautiful and super important in higher mathematics. They're definitely worlds that we want to know about. And one of the first things a mathematician will ask about these little worlds is how solving equation works in those worlds. Equations are how we ask and answer mathematical questions, right? And now Gauss's golden theorem appears. It turns out that quadratic reciprocity leads to a very unexpected, very simple, and very beautiful connection between the solutions of quadratic equations in completely different mini-fields. Crazy stuff, but also very important stuff for understanding these worlds. That was a little side trip to peek at the very surprising geometry of finite rings, but let's get back on the road to the main attraction. We'll begin by looking at the algebra of these worlds. It turns out that finite rings are incredibly useful for investigating the integers and in particular the prime numbers. Is that surprising? Here's an easy example which may also be very familiar. What happens if you divide an integer by 2? Yep, you just get a remainder of 0 or 1 depending upon whether the number is even or odd. But this means that the Z2 tables capture the algebra of even and odd numbers. There, replace all the zeros by even and all the ones by odd and voila! Those are all the familiar rules about adding and multiplying odd and even numbers. For example, an even number plus an odd number is odd. Odd times odd equals odd, and so on. As you probably know, this capturing of even and odd is incredibly useful. And since splitting up the integers into two classes according to division by 2 is so useful, it would hardly be surprising if splitting according to division by other integers also led to important insights, right? And that is indeed the case. Let's look at a few interesting quadratic insights, a couple of roadside attractions along the way to quadratic reciprocity. Quadratic suggests squares. So let's have a look at squares in our mini-rings and see what they can tell us about the integers.
All right,
That means we're looking at multiplication and in particular at the diagonal.
All right, until next time.